Good morning. So today's lecture will be summative example. So we will discuss the overall example or real practical problem to apply what we have learned in this course. So we want to build a digital logic circuits using all of what we learned before in real practical example. Quiz 5 will be on Friday, and it's going to be open notes from lectures number 19 until 22. All of the lectures after the second exam, all of them are included. So you need to focus on the lecture notes, homeworks, and see the problems. It's open notes. You don't need to worry about memorizing anything. Make sure to understand them. Okay? So in the summative example, we will see a practical problem, which is traffic light controller. So as an engineer, so they ask you, for example, you need to design a traffic controller into a certain area, into a certain intersection. So your role as an engineer to design this, or as a programmer to design, how can we make these circuits, how can we program this traffic light controller? So let's imagine this scenario. We need to design a traffic light controller for two-lane intersection. We have, let's call it north, south, east, west. Okay? Then we need to understand or make some assumptions. The first assumption, which is we have each state, we have called a clock pulse. The clock pulse comes every 10 seconds, and we have a reset button. So in case we want to reset the traffic lights. So how many lights do we have? Since we have south, north, west, east. So this traffic lights of east and west will be the same, and south north are the same as well. Okay, they're all the same lights. We will not assume there is any arrows like green arrows. We will assume only the basic traffic light that has only 3. So we have one traffic light here, one traffic light here, one for east, one for west. So basically, east and or south and north will turn on together. East and west will turn on together, right? They should be synchronized together. So what are the options? We don't need to make one traffic light for east, one traffic light for west. We'll keep them as, we will call them as north-south or east-west. So we will assume like that we have two systems, two separated systems. The first system with north-south, the second system with west or east-west. Okay? Then each traffic light has 3 lights, which is red, green, red, orange, or yellow. Let me call it yellow. Yellow, green. So for red, we will denote it by R, yellow Y, green G. Since we have 2 systems, we will say there is R, north-south, red for north-south, red for east-west. There is a yellow for north-south, yellow for east-west, and so on. Green for north-south, green for east-west. Okay? So we should expect 2 outputs. Which are the outputs? 6 lights. They are actually 12 because one of them for the north, one of them for the south. But I don't need to repeat them since the north and the south are the same. Then I'm mixing them with one variable. So we have a green north-south, yellow north-south, so here, red north-south, a green east-west, yellow east-west, red east-west. Okay? It's simple. So how can I make this into a state diagram? The state diagram, we can make several states, as shown here. So state number A, when green north-south is on, Okay, the green is on. What will happen to the other light? Should be red, right? So in this case, also green north south is on, then red east west are on, is on as well, right? The rest will be off. So this is state A. That's why I call it state A, and I call it GNSREW, which means what are on here. Okay? How about state B? For state B, when it's green and red, green, the other traffic light is red. So I wait 10 seconds, then I will move to the next state, which is yellow and red, right? So this one should be yellow. Yellow, north, south should be on. And the other side, of course, must be red, right? This happens after clock, which is after 10 seconds. So I assume that each clock will happen after 10 seconds. So I move to state B, and the rest off. So it will continue in yellow for 10 seconds. After that, state C, the next state, which is the north-south, will be turned to red north-south, and east-west will be green, right? So here is on, here is on. Then the rest are off. Now, the other side is green, while the north-south side is red. What's the next state? So this one to be yellow, right? Yes? Okay. So north-south will remain red, while the green the east-west, the green will turn to yellow. East-west will be on. Then the rest off, right? After that, what's the next state? The yellow will turn to green, which is state A. So I will back to state A. That's why I have A, B, C, D, then I'll back to A. Okay? So it's very important to understand how to do this, which is basically just the traffic rules. I assume everyone can have a driving license, so everyone are familiar with the traffic rules. So, understood? But let's have, by looking at this scenario, we will see that the green here takes 10 seconds. The red or yellow takes 10 seconds. The red takes 20 seconds, right? By this assumption. Is that right? So sometimes we can say it's inconvenient to have 10 seconds for green, 10 seconds for yellow. Sometimes 10 seconds might not be enough. Can we extend it? Yes, we can. So we can say here, it's too short for the green lights. We can add another state, which means after the first state here, green, I want to keep it green, adding a transient state here or a state in the middle to keep the green green on for another 10 seconds. So make it 20 seconds, which is the same as this table, but we will add another state in the middle. We will sit here in the middle to make sure the greens are on. That's what we did here. This is the same as the original, those 4, and the new here. So I call this one A1, this is A2, this is C1, C2. So for A2, the green is just an extension, the same as A1. Exactly the same, which is just to extend the green to add 10 more seconds for the green. And here, add 10 more seconds for the other green. Okay? So in this case, I can guarantee the green time can be extended. We can have, in this case, the green 20 seconds, the yellow 10 seconds, but on the other hand, red will be 30 seconds. But I give more time for the green, so the green will not be too short. Okay, understood? Any questions? Now, let's call this state. When we say that when the green is on or red is on, we will replace on by 1, we will replace off by 0. Okay? Can we write them into a state table? Yes. Let's try to make a state table for this part, for the new one. The first state, let's assume it's state A, A1. Here the green north-south is on. Here's green north-south is on. So this table, I can tell it, the green north-south is on. So I'm going to pay north-south is on. And the red east-west is on. Red east-west is on. While the rest are zeros. 0, 0, 0, 0. So here I'm with state A. If the clock is not finished yet, I will remain at A1. If the clock is done, I will go to A2, right? Do you understand how I write this? Again, how did I do this? On the state table, at state A, the green north, on here, the green north-south is on, red east-west is on. The other lights are off. So this one, the other lights are zeros. While for the states, if the 10 second is not finished yet, it will remain in A1. If the 10 second is done, I will go to A2. Okay? And so on. That's how we will do for the rest. For A2, the green north-south is on, red east-west is on. So here is 1, 1, and the rest are zeros. If the clock is not done, I will remain in the same state. If the clock is done, I will go to the next state, which is B. Right? Now at state B. State B, the yellow is on, and the red is on. So here's the yellow north-south is on, the red is on. The rest are zeros. How about the clock? If the clock is not done, I will remain at B. If the 10 seconds is done, I will go to C1. So if it's not done yet, I will remain at B. If it is done, I will go to C1. Okay? Now I'm at C1. Here's C1. Red north-south is on. Green east-west is on. So here is red north-south is on. Green east-west is on. Then the others are zeros. Then at C, if the clock is not done yet, the 10 seconds is not done yet, I will remain at C. If they are done, I will go to C2. So here is, I will remain at C1. If it's not done, if it's done, I will go to C2. Okay? At C2, red north-south is on, green east-west is on, which is similar to C1. And the other are zeros. When the clock is not done yet, is not finished yet, I will remain at C2. If it is finished, I will go to D. So here is C2, here is D. The last state, D. Red north-south is on, yellow east-west is on. Red north-south is on, yellow east-west is on. The others are zeros. If D is not finished yet, I will remain at D. When D is finished, I will go to A1. Okay, is this clear? Now, we actually converted this problem, this practical problem, to a state table. You see? Now, then we can apply the digital logic circuit that we've done before. Okay? So how can we do this? How can we make it into a digital logic circuit? The first step, we need to assign a numerical value for the states. How many states do we have? 1, 2, 3, 4, 5, 6. 6 states. Okay? And let's recall, 2 power number of flip-flops will equal to states. Is there anything 2 power something equal to 6? No. Right? There is nothing. So how about if I say 2 power 2 would equal to 4? 2 power 3 equal to 8. So what should I use?
You're going to use 2 power 3 because that's the closest thing you can get.
Yes. I can use 2 power 3 because it will cover the 6. It will cover the 6 states. So this means I will have some extra that I will not use. Extra states that I don't need to use. So I need to use 3 flip-flops. 3 flip-flops. With these 3 flip-flops, I can assume them as y2, y1, y0. Okay? Now, since I said we have 3 flip-flops, so bits y2, bit y1, bit y0, I need to assume or to make values for each variable. So let's make this assumption. We have A1, A2, B, C1, C2, D. Let's assume the corresponding values for A1 are 0, 0, 0. You are free in this assumption. You can make any assumption you want. But I'm going to try to make them as more convenient for us. So let's try to make them as an order. So 0, 0, 0. Then here 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Okay? So this is more convenient sequence for us, so it can be easy to follow. Then what I need to do is to replace this sequence or replace the variables by this sequence. So instead of mentioning next state or present state as variables, I'm going to replace them by these numbers. So basically, we will redraw the table as shown here. The green, yellow, the outputs will not be different, will be the same as what we wrote here, but the only difference is this part. Replace this part. So, in this part is A1. So A1 is actually 0, 0, 0. Here is next state A1, 0, 0, 0. Here is 0, 0, 1. 0, 1, 0. 0, 1, 1. 1, 0, 0. 1, 1, 1. I'm sorry, 1, 0, 1, right. 1, 0, 1. Okay? Then here, the next state will be 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, then here 0, 0, 0. Just substitute the variables, the corresponding variables based on this table that we did. Then we will get this table. Okay? Now we are ready to do the state table or to do the equations. So those are the states. Do we have any inputs? Yes, a clock. Inputs. And we have states and outputs. So in order to do the analysis, we need to make kernel maps for states. We need to make kernel maps for y2, y1, y0, and we need to make also kernel maps for outputs, which is GNS, YNS, RNS, GW, GEW, YEW, REW. So actually I need to make 1, 2, 3, 4, 5, 6, 7, 8, 9. I need to make 9 kernel maps for each variable, because again, we used to do in our design problems kernel maps for the states and kernel maps for the outputs. And when we used to do kernel maps for the outputs, actually it was the easiest part, because in the outputs, make the kernel maps, then we don't need to worry about which kind of flip-flops do we need to do. While on the states, make the kernel maps first, then assume the equation or assume a flip-flop, and add the equation for that flip-flop. Try to make this equation match with your flip-flop. So when we work with the states, it will take some time. While when we work for the output, it will be easy. Okay, so can anybody tell me, what do you think the size of kernel map will be? Yes. Do you think? Any suggestion? The size of the kernel map. Will it be 3 variables, 4 variables, 5 variables, 2 variables, 1 variables? To answer about this, let me redraw the state table on the general formula that we used to do. Okay? So the general formula, or the general state table, here is y2, y1, y0. See, here is present states. Here is inputs. I'm gonna write a clock, or let me denote it by x. Then here is next states, which is y2 star, y1 star, y0 star. Then there are the outputs. Okay? So we can say this is 0, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1. Okay? Then let's continue. 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1. Okay, it's large table. 1, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. Okay? So based on that, how many inputs do we have? Or how many kernel maps? What do you expect about the kernel maps? 4, 1, 2, 3, 4. 4 variables. So we can say this is 0, M0, M1, M2, M3, M4, M5, M6, M7, M8, M9, M10, M11, M12, M13, M14, M15. Okay? So what do we expect about the next states? Just try to translate this table to here. So here when it's 0, 0, 0, the input clock is 0, it will remain at the state which is 0, 0, 0. When it is 1, it will go to 0, 0, 1. Here it will 0, 0, 1. Here it will be 0, 1, 0. Then 0, 1, 0. 0, 1, 1. Then here 0, 1, 1. Then here 1, 0, 0. 1, 0, 1. So here 1, 0. In this states, after 1, 0, 0, it will be 0, 0, 0. Okay? So by drawing this, we're done with, we have written the table for the states until here. But what will happen to the rest? By translating this table, it will be only this part. What will happen to the rest?
0, 1, 0, 0, and go to 0, 1, 0, it should be the 1.
Okay, 1, 0, 0, right. Then here will be 1, 0, 0, then here 1, 0, 1, then here 0, 0, 0. Is that right? Let me.
1, 0, 1.
Okay. Now it should be correct, okay? Now we have some elements are left. Why do we have this?
Because we don't care about them. It's all the extras that we had resulting.
We have the extras, right? Because it should handle 8s, but we are using 6. In this case, we don't care about them. Since we don't care about them, what should I write? Don't care. Don't care. Sometimes I donate it by D or by X. It doesn't matter. We will put D, 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 D. Okay? How about the outputs? GNS, YNS, RNS, GEW, YEW, RNW. So it's gonna be here 1 0 0 0 0 1, and here 1 0 0 0 0 1. It will be 1 0 0 0 0 1. Then it will be 1 0 0 0 0 1. Then 0 1 0 0 0 1. Again 0 1 0 0 0 1. Then 0 0 1 1 0 0 0 0 1 1 0 0. Then here will be 0 0 1 1 0 0 0 0 1 1 0 0. Then the last one 0 0 1 0 1 0 0 0 1 0 1 0. And this area is don't care, so we will make them don't cares. D D D D D D D D D D D D D D D D D D D D D. Okay? Do you agree with me about this table? Okay. Now, here is the kernel maps. We can apply kernel maps here. Let's make kernel maps for the states. Let's work for the states. And the states, which is y1, y2, y3. We have 3 states. Next state, y1 star, y2 star, y0 star. Then we need to make 3 kernel maps, 4 variable kernel maps. Okay. And the variables are y2, y1, y0, x, y2, y1, y0, x, y2, y1, here y2, y1, y0, x. So here is 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Then here 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Then here we will say this is y2, here is y2, here is y2, here is y1, here is y1, here is y1. Then this part is y0, y0, y0. This part is x, this part is x, this part is x. Here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay? Now it's the time to write the kernel maps or the variables. So here, where are the location of ones at y2? So this is for equation for y2 star. Here is y1 star. Here is y0 star. Let's look at y2. It's ones. It is 1 at M7 Here is 1 at 7, 1 at 8, 1 at 9, 1 at 10, and we will see from 12 until 15, don't care. 12, don't care, 13, 14, 15. Okay? How about y1? Let me look at the ones which is at M3, M4, M5, M6, then don't care at those points. How about y0? Y0, the location at M1, M2, then M5, M6, then we have M8, M9, and don't care at this row. 13, 12, 13, 14, 15. Okay? Is this clear? Now, let's try to find the equation one by one. So y2 star. How can we group the flip-flops? Again, the don't cares are not necessarily to be added. So we are trying to make a group of 16. There is no way. A group of 8, no way. A group of 4, is there a way to make a group of 4? What do you think? Yes, we can make a group of 4 here, right? Can we make another group of 4, including the ones? No. Group of 2, yes. How about this? Group of 4, is there a way? Yes. Group of 2, here. How about this one? Is isolated. Okay, how about this? Here, X or don't care, they are the same. Group of 4. Yes, here and here. Here, can I make a group of 4? No, there's group 2. Okay? Now, let's write the equations. So we have y2 star equal to, what's this variable?
The bar0 or y0.
y2 times y0 bar, right. Plus, how about this pair? Which is located at y1, y0, x. And how about this? Located at y2, then y1 is not, y0, x bar. Okay? How about y1 star? y1 star, this section is for y1, or here y1 and y0 bar, this square. y1, y0 bar, plus this pair is associated with y1, y0, and x bar. The last element should be including four variables, which is this is y2, so y2 bar, y1 bar, y0x. Okay? Now this Carnot map for y0 is going to be, we have set of 4 here, which is y, this is y2, y2, y0 bar, plus this set of 4 is y0 bar times x, plus these two are associated with y2 bar, y0, not y1, and x bar, right? Okay? Now I found all of the equations for the states. My desire to use flip-flop, JK flip-flop. What's the JK flip-flop equation? Is to make Q star equal to k q bar plus j q bar, plus k bar q. So can I make this to be in j2 y2 bar plus k2 bar y2? Is there a way? Let's see. So here is y2, that's fine. Here is with y2, that's fine, but there's a problem with this term. It does not include either y2 or y1. So what I'm gonna do, I'm gonna make this to be y3 y0 bar plus y1 y0x times y2 plus y2 bar plus y2 y0x bar. Okay?
It's y2 times y bar, y0 bar.
y2 plus y2 bar.
The first one, y2. First one.
First one, yes, y2. Why did I need 3? Thank you. Then we will say that since here we have j2, j1, y2, so we can say the j2, the thing that has y2 bar, so this is not y2, there is y2 bar, which is y1 y0x times y2 bar plus here is y2 plus y1 y0x plus y2 y0x bar times y2. Okay? Then we have some simplification using algebra. We will end up having y1 y0 y2 bar plus here after doing algebra, because x with x bar will be 0, then we will have only y2 y2. I'm sorry, this is y2 y0, I'm sorry. Okay, so as a net, this will equal to j2 y2 bar plus k2 bar y2. This means j2 equal to y1 y0 and k2 will be y0 bar. I think no, k2 will be y2 not y0 bar, so here's the bar here. Okay. How about this one? So here is y1 y1 and this is y1 bar. So it's already been ready in the flip-flop, which is j1 y1 bar plus k1 bar y1. So we can say, where is y1 bar here? So we have y2 bar y0 x times y1 bar plus k1 bar, which is y1
times the y0 bar
plus this part is, we said it's y2 y2. Okay, I think I get confused about something here. So where is the y1 bar? We already did this here for y1
times the y0 bar plus y0 times the x bar.
Okay, so which is here the first one, which is y0 bar plus y1 times x bar, y0 times x bar, right? That's it or no? Let me do it again. Where is y1 bar component, which is this part? So here we have y2 bar y0x, all of them times y1 bar plus, now we need to have the y1, this one, which is y0 bar 0 bar plus y0 x bar times y1, and we can make some simplification because this is actually equal to 1. or I think we can make some simplifications, which is gonna be I think y1, y0 here is bar times y1 plus y2 y0 whole bars times y1. So in summary, J1 will be y1 bar y0, K1 will be y2 bar y0. The last one, how to make this simplification. We need to make it again JK flip-flop. How can I make it J0, y0 bar plus K0 bar y0? So basically it's going to be group the bars here, which will be y2. Then here we have here is y2 bar, yes, just y2 times y0 bar plus k0, which is x plus y2 bar y0. Here we already have y0, x bar. Then this times y0. Then after making the shortcuts, it's gonna be y0 times 1. There are some simplification can be done. Plus 1 y0. So we can say j1 will equal j0 equal to 1, k0 equal to 1.
The j will be equal to y2 plus x times the y0 bar.
Yeah, but after doing some simplification, y2, y0, y2 bar, y0, then we can make some simplification actually. I mean, we can make some algebraic theorems to do that. I mean, if you stop at this and say this is j, this k, that's fine. If you do the simplification, that's fine. I mean, either way, this is correct and this one's correct, and the same for the rest. When we did the simplification, if you don't want to simplify, that's fine. I mean, if you stop at here, that's right. But the textbook simplify it. That's why I simplify it here. Okay. Now we're done with the equations associated with the states. How about the outputs? The outputs, how many outputs do we have? 1, 2, 3, 4, 5, 6. So we need to make 6 Carnot maps, 4 variables. Oh, it's gonna be tough. But let's have a look. We can make a small shortcut. Let's look at the small table. We can see the outputs is not a function of inputs. You see? Does not change by the changing of the inputs. So we can actually use 3 variables Carnot maps. We don't need the 4th variable. Why? Because the outputs is not a function of inputs. So here, outputs is not a function of inputs. So we can use 3 variable Carnot maps, which are associated for the states. Then we can go back to the table number 1. This table. We can say this is M0, M1, M2, M3, M4, M5. Since it should be 7, then we have M6, M7 are don't cares. So we can simplify the problem. You can still use the 4 variable Carnot maps, that's fine. You can still use it. But sometimes some shortcut can happen. Again, this happens only for this example because this is very special. I don't expect to see this in the test, so don't worry about it. How can we make the flip-flops? Or to make the Carnot maps, let's try to make Carnot maps for each one. For y2, or for green north-south, it's at M0. Let's look at this table and put it here. It's for M0 and M4. Then I don't care at 6 and 7. Here's, I'm sorry, M0 I think M0, M1. Then 6 and 7. 6 and 7 are don't cares. So basically, we can say that this is the loop. And it equals to what GNS will be. This is Y2, here is Y1, here is Y0. So it's going to be Y2 bar, Y1 bar, right? Okay, how about yellow? Yellow at M2, only at M2, and 6 and 7 don't care. M2, 6 and 7 don't care. Then we can group these. So this is going to be Y1, Y0 bar. Again, this is Y2, here is Y0, here is Y1. So Y1, Y0 bar. Okay? Let me write it here so it can be clear. Y1, Y0 bar. Now, for the red, north-south, it is at 3, 4, 5, 3, 4, 5, and don't care at 6 and 7. So, we can group these 4, or we can yes, we can red, north, south. We can group these 4, and we have these 2. So basically, it's going to be 1, or here is Y2, here is Y1, here is Y0. So it's going to be Y2 plus Y1, Y0. Or sometimes as a shortcut, north-south, or the red is the opposite of yellow and green. So we can use this, or we can say red north-south is green north-south plus yellow north-south nuts. Whenever those are not working, the other will work. So you have either ways. You can use this one or use this one. Okay? How about the green east-west? Green east-west at M3, here is green east-west. At M3, M4, then 6 and 7 don't care. M3, M4, 6 and 7 are don't care. Let me check again. Is it M3 and M4? M3, M4, 6 and 7 don't care. Okay. So we can group these 2. How about this? How can we group it? Okay. We can group it in the other side. Then we'll end up having, will be Y2, Y0 bar plus Y1, Y0. How about the yellow? The yellow, east-west, it is at M5, then 6 and 7 don't care. M5, 6 and 7 don't care. So we can group only these 2. And it's going to be Y2, Y0. How about the red east-west? I have 2 options. The first option by making the kernel map, or make this the opposites as what we used to do here, as we did here. So we can say R east-west, red east-west at 0, 1, 2, then 6, 7. 0, 1, 2, 6, 7 are don't cares. So we can make these 2 together, these 2 together, right? So here is Y2, here is Y1, here is Y0. So it's going to be Y2 bar times Y1 bar plus Y1, Y0 bar, right? Or we can say red east-west is actually the green east-west plus yellow east-west bar, because it should work when they are the opposites. Okay? So what should we do then? After writing the equations, we already have all of the other equations. So we have, in summary, we have the JK flip-flops. So we have y2 star equal to j2 times y2 bar plus k2 times y2, such that j2 equal to what's y1 y0, k2 equal to y0, then y1 star equal to j1 y1 bar plus k1 bar y1, such that k1 j1 equal to y1 bar y0, k1 equals to y2 bar y0, then y0 star equal to j1 y1 bar j0 y0 bar plus k0 bar y0, such that j1 equal j0 equal 1, k0 equal 1. Then the last scenario, or writing the output equations, which are G and S equal y2 y1 all are bars, y and S equals to y1 y0 bar, R and S equal to G and S plus y and S all bar. Then we have G east-west EW equal y2 y0 bar plus y1 y0, then W or y east-west equal to y2 y0, then red east-west equal to G green east-west plus yellow east-west all bars. Then with these equations, make them to plots to make this plot. So we can build this design, connect the clocks, connect the resets, make JK flip-flop, the defaults, make its rising edge, and that's it. Then we can construct this design. After making this circuit design, I can go to the lab, make the integrated circuit board. Then I can say this integrated circuit board can make the traffic light systems. So now the traffic light system is ready. Then I can test it. So this one of some complicated examples about the practical applications of digital logic. So we can make a traffic light system. One of the examples you can see also in the textbook, which is how to make a machine that you can buy ice cream machine by 25 cents or something like that. Then how you can insert the coins and see how you can build the system. These kind of complicated problems, they will not be in the test because it will take a very long time. It will take the whole test to do that. So those are kind of project-based, but since in this course we don't have a project, then I'm just trying in this lecture to explain it to you to make sure that you understand, or you know why we learned or why we studied all of these techniques, why we studied in the beginning digital logic, or why we studied the AND gates, OR gates, the number systems, why we discuss about the flip-flops, why we discuss about state diagram, state table, why we discuss about the kernel maps. So this is the lecture. This lecture name is Summative Example, which is sum everything we covered in this class. So what you need to know is to understand the procedure. You don't need to memorize anything. You don't need to do all of these technique at one example. This will be too much, will be very hard. and you will spend maybe the whole exam in doing one problem. So make sure to understand how we did this. So maybe in the future, if you when you work, maybe you might see some kind of these problems. So at least you have a clue, or you have you have maybe an overview how to deal with these kind of problems. So